Hi, everyone. Welcome to the new and old room. Finally, we get to have talks here. The board is fixed. All is good. And I'm very happy to have Jeroen Zuiddam with us. He was postdoc here 5, 6 years ago, roughly.
Yeah.
And he works on things that are really beautiful and based on deep mathematics that is not very well known outside of that group of people in algebraic complexity. But luckily, he's just completed a survey with Avi on asymptotic spectra. So that's something people can look at. And even more luckily, he's a fantastic speaker. So we're very happy to have him talk to us.
Now I have to perform. Well, okay, so I'm very happy to be back and to talk to you about this area of work. So I'm going to talk to you about asymptotic spectrum and approximation approaches to direct sum problems. And the motivating question in these sorts of in this theory is what's the cost of a task if we have to perform it many times? Yeah, and it's a type of question that you've probably seen because it appears in many places in mathematics or computer science or physics. Sometimes it's called direct sum problems. You can call it economies of scale, or you can just talk about savings. And mathematically, often the way this will appear in how I think about it is that we're interested in some task T, and when we're doing it multiple times, it corresponds to taking a power. So we're going to take an nth power, whatever that means. So I will make that more clear in specific instances. And then we have some complexity measure f, and we want to understand how does this complexity measure grow when we take n to infinity and we normalize in the appropriate way. Okay. So I'm going to talk about two specific such problems, and the first is called the Shannon capacity of graphs. This problem was posed by Shannon in 1956, and it's motivated by zero-error communication. And it asks for determining the rate of growth of the independence number under strong graph powers. I'm going to explain more precisely what all these words mean later. A wide range of upper and lower bound methods have been developed for this problem. By Shannon himself, and then Lovaas with this theta number, Hamers, alone schrijver. And recently, so companies like Google DeepMind tried to build their machine learning to try to solve these problems or see if they can make progress on these kind of problems. So far, the humans are still winning at this problem. Okay, so it's some sort of benchmark, I guess. Despite all this interest, even small instances of this problem have remained open. So for example, for odd cycles of length at least 7, so already the 7th cycle, this problem is open. Okay, so I'll explain later all the definitions so that you understand. Okay, second problem is fast matrix multiplication. Here the question is, what's the fastest algorithm to multiply n by n matrices? And Strassen in 1969 gave an algorithm that does this in big O of n to the power 2.8 operations. That was a big breakthrough at the time. Before that, there was nothing that went below like n cubed. And since then, many new ideas, upper bounds, barriers have been developed for this problem. Many people, Schoenhager, Koppers-Winograd, Stodders, Lecal, DeepMind, again, Vasilevska, Williams, Allman. So it's a very active field. Many of these people, or many of the younger people are at Science Institute, actually, where I'm also now these months. Now, so currently, the best upper bound for this question is n to the power 2.37.
Humans are winning.
Sorry?
Humans are still winning.
Humans are still winning. That's correct. Yes, that's right. We're still winning. This is the best bound. The best exponent is still open. Good. All right, so we have these two problems. They look quite different, and they are quite different, but they have a similarity, and that's at first looks maybe superficial, but I'll explain to you, or you will maybe see how this is actually a deeper type of similarity. So in the Shannon capacity problem, I already said we're studying the asymptotic behavior or the limit, or like the rate of growth of the independence number under taking graph values. So it's called the Shannon capacity. In the fast matrix multiplication problem, you can actually transform this into a problem about tensors. I'll explain this more. And you want to understand the rate of growth of tensor rank under taking powers of your tensor. It's a specific tensor that you care about, but you can ask this question for any tensor. What happened after Strassen? Well, lots of things happened for matrix multiplication. One thing that happened is that Strassen in the 80s came up with a duality theory that he developed to understand matrix multiplication. It's called asymptotic spectrum duality. And I'll explain to you more what this is. But it characterizes, it's a theory to characterize like the best exponent of matrix multiplication. And not much happened after that. So this was kind of a hidden gem, maybe, or like a hidden theory. Not much people worked on it until a couple of works, also by me. So we got some more understanding in 2018 about this connection, and also I understood how you could apply this to some other problems, including the Shannon capacity problem. Yeah? So this theory that first applies to algebraic complexity apparently also applies to the Shannon capacity problem. And since then, there have been many more applications. So Avi and I wrote a survey, as Reed already mentioned, on this theory and the various applications. And there have been more. So together with Robert Robert, who was also a postdoc here together when I was here, we found some applications in circuit complexity, and recently, actually last week, Alman and Lee had a new application on depth-2 circuits with this type of duality. So that's also really interesting to have a look at. And one hope is, of course, to solve these problems, but also to carry over ideas from one problem to another. So maybe we can have some ideas here that work well for Shannon capacity, and we can carry it over to matrix multiplication or the other direction. Yeah? And that's a bit of the flavor of what I'm going to do today. So one goal of today is to give some introduction to asymptotic spectrum duality. And another goal is to talk about some recent developments in this area, and they have to do with approximation and limit approaches. Here, what I want you to think about is that maybe we want to understand the Shannon capacity of some target graph G, some hard graph. Maybe it's the 7 cycle. It's like a really small graph, but we don't know what its Shannon capacity is. And what we could try to do is maybe construct a sequence of other graphs, G1, G2, etc., that are easier to understand somehow, and that converge to G in some notion, which we have to discuss, of course. Like, what should that be? Well, one property that convergence should have is that the Shannon capacity then also converges. Okay, so I'm going to explain to you a notion later in which that actually happens. So that's an approach. And we might want to try to do a similar thing with tensors. So in the matrix multiplication setting, maybe we want our target tensor is the matrix multiplication tensor. We don't really know how to attack it directly. Maybe we can construct a sequence of tensors that's like converging to the target tensor. Okay? We have to think about how, in such a way that the asymptotic ranks have to be easier to analyze, in such a way that the asymptotic ranks also converge or have some sort of semi-continuity. Okay. So this is the outline of the talk. So I'm going to start with Shannon capacity and explain in that context the asymptotic spectrum duality. Then I want to talk about convergence in that setting. It's going to be convergence in asymptotic spectrum distance. So I'm going to explain this distance. Then we see, kind of as an aside, how infinite graphs arise as limit points. Right? Once you have convergence, you can start asking these sorts of questions. And then I will briefly say how this whole business gives new lower bounds for the 15 cycle. So it's not the 7 cycle, it's a bit larger, but yeah, okay. And then I have to see how we're going to do in time. But then I want to talk about tensors and asymptotic rank. Matrix multiplication, explain it in a bit more detail. And then I want to talk also about the notion of convergence there. It's a different notion that I want to talk about. It's convergence in Euclidean distance. And we're going to see what comes out of that. Okay. Any questions?
I think omega equals 2 or
Do I think omega equals 2?
Yeah.
Yeah, I hope omega equals 2. Yeah, I think it's a good target. Yeah. It's a good question. Any more questions?
What about PNNT?
Yeah, that's where my expertise is. Okay, good. Okay, so let's start with Shannon capacity. So I want to start with the basics. So we're really going to see how this works. Right, independent set, maybe you know. So you have a graph, independent set is a subset of the vertices that doesn't induce any edges, right? And we can ask for the independence number of a graph, which is the size of the largest independent set in the graph. So in this 5 cycle, it's 2, and in this kind of star is 3, and we denote this by alpha, called independence number. Then there's a natural notion of product in this Shannon capacity setting. It's motivated by communication. It's called strong product, denoted by this box. I usually explain it as follows. It's the graph whose adjacency matrix is the tensor product of the adjacency matrices of G and H. Yeah? So you have your adjacency matrix of G and H. I always put 1s on the main diagonal. That's just what I do. And then I take the tensor product. That's the end product. Okay? Or Kronecker product, end product. Okay. And then there is a notion of ordering. And if you're into complexity theory, you should think of this as a reduction, notion of reduction. Yeah, just like we can have reductions between computational problems, this is kind of a reduction between communication channels in the end. It's called co-homomorphism. We say G is at most H if there is a map from the vertices of G to the vertices of H, preserving independent sets. Or you could also say preserving non-edges. Yeah, so if you have 2 vertices in G that are not an edge, then when you map them to H, they should still be not an edge. Okay. Good. It's a natural ordering because we care about independent sets. So it's natural that we want to preserve these. Now, the Shannon capacity, I already mentioned it before, is this limit, right? So we're taking G to the n, independence number, and then we take the nth root and let n go to infinity. Yeah, so it's a rate of growth. There's a lemma called Feket's lemma that says that for these kind of parameters, you can replace limit by supremum. It's kind of a general lemma, so it's not very deep. But it says that it's you can either do limit or supremum. You get the same. So you might think of Shannon capacity as a maximization problem. What I want to say, trying to maximize this normalized independence number of a power. Now here's the duality theorem. So it goes back to Strassen. I applied it to Shannon capacity. What it says is that this maximization problem, the Shannon capacity, we can also write it as a minimization over some class of functions called capital X. We take these functions f and we just evaluate it on G. Okay. So we have maximization and minimization. Now, what's this set X? Hopefully it's a nice set, otherwise we haven't achieved much. So it's called the asymptotic spectrum, and it consists of functions that go from graphs to the reals, non-negative reals, that are multiplicative under the strong product. They're additive under disjoint union on graphs. They're normalized to 1 on just a single vertex, K1. And they're monotone under cohomomorphism. So if G is at most H, then f of G is at most H. Yeah. So it's like, like monotone functions that have these extra algebraic properties.
Sorry, can you repeat? What is the third one? K norm.
K norm. K1 norm. So K1 is the complete graph that is just one vertex. That's what K1 means. Normalized means there it has to have value 1. And because of additivity, it also means that if you just have a bunch of points, no edges, so if you have R points, then your function must have value R. That's what I mean. Okay. So here's a question. Maybe not such an easy question actually. Does anyone have an idea of what kind of function is in this set?
Theta? The Lovas-Theta function.
Lovas-Theta function. That's right. Yeah, that's an example. Apparently it has all these properties. So that's already, I think that's already in Lovas's paper. Like you can find all these properties there. So it's from 79. Any other ideas? Other nice functions on graphs?
Alpha itself.
Alpha itself, no, alpha is actually not in there. And it's because of this, for example, this one. Well, alpha is additive, that's right. But it's not multiplicative. And that's kind of what we're interested in. Like in how much is it not multiplicative? That's what we're trying to understand with the Shannon capacity. But you're right, it's good to check that. And yeah, already for the 5 cycle, it's not multiplicative.
So this should be an infimum and not
A priori, you would think that, and then you start studying this set, and you will notice that in the right topology, it's a compact set, in such a way that this is a minimum. You can put a minimum.
So there is some function that at least mimics the Shannon capacity for our graph. It's the same value as the Shannon capacity on
That's
our
right.
graph, but it doesn't give the Shannon capacity on other graphs.
That's right. That's right? So that's the order of quantifiers. So you fix your graph, and then you find this f. That always works. So in that sense, it's like a complete set of upper bounds. Sorry, like all these functions are upper bounds. It's a complete set of upper bound techniques. There's no barrier for these kind of functions to reach your target. And related to this, the Shannon capacity is also not in the set X. So that's right. Yeah.
Do we know this prim can be replaced with max, like in the definition of Shannon capacity?
It cannot be replaced by max.
Oh.
There are examples. You can take the 5 cycle and a single point as your graph, and there you have to do a supremum. It's an example.
So you can just count vertices, right? That's also.
It's a good initial guess, but then because I'm doing this.
Is it monotone? Yeah.
Yeah, exactly. I'm doing this monotonicity under cohomorphism, and cohomorphism is kind of interesting. It does not need to be injective. I just need to preserve non-edges. So I'm allowed to collapse edges, for example. So number of vertices is not part of it. But I think the most related is called the fractional key-covering number. It's like the closest to the number. It's like the closest to what you're saying. That one is in there, for example. It's the complement of a fractional chromatic number. Okay. So what examples do I have? Lovas-Theta, fractional Hammersbound, some sort of min-rank parameter. The fractional key-covering number. They're not finitely many. There's infinitely many. And there's lots of interesting things to say about that, which I won't have time for, but I'll talk about it some other time. But we have examples, but we don't know the full set. Well, we don't know if we have the full set. That would solve the Shannon capacity problem, right? If we have an explicit enough description. Okay, so that's the duality kind of statement. I want to now use this, right? Because I had this idea of, can we make sequences, converging sequences? So let's make a natural notion of distance. So we have this asymptotic spectrum. I want to make an asymptotic spectrum distance. So I have G and H, and we define the distance by going over all these functions and using those to to measure distance. So I take the maximum over these functions and I look at how different are their evaluations, right? It's called the max norm or sup norm. It's natural. If you have these functions, this is what you want to do. And so let's have a look. Is this a good idea? So this is the definition again. Well, we want to have this, right? We want to have that if our graphs are converging in this distance, then, well, I would hope that the Shannon capacities also converge, because that's our goal. So let's give a quick proof. So let epsilon be bigger than 0. So, right, these distances are converging. So we have a capital N, so that for I bigger than N, for any spectral point, it's called spectral points, their distance on Gi and H is at most epsilon, starting point. Okay, now let's take functions f, Gi, and fh in the spectrum, so that achieve the Shannon capacity for Gi and for H, right? We already observed that apparently you can do this. That's the duality. Then here comes an inequality. So we have the Shannon capacity of H is fh of H is strictly bigger, that's because of this statement here, than fh Gi minus epsilon. This fh, it's some function in the spectrum, so it will give an upper bound on Shannon capacity. Maybe it's not optimal, but I can lower bound this by Shannon capacity and then minus epsilon. And you can do the same with H and Gi swapped. So then we're there, then we're done. So we have this relation between the Shannon capacities with this epsilon.
So you use here the fact that the infimum is a minimum.
I'm using this here, but I don't know if you really need it. Second.
Could have even give like without the upper bound thing, just the fact that on every function the epsilon agree, you could have got here minus 2 epsilon.
Yeah.
Just by using this one, not an upper bound.
Okay, so this is good. Now let me just, so it has a bit of an abstract definition. Can we also make a more constructive description? And here is one, so the following are equivalent. So this distance is at most A over B. If and only if you have this inequality, where this is, remember, this homomorphism inequality. So on the left, I'm kind of blowing up the left side and the right side. So here I have B copies of G, take an nth power, and this should be at most B copies of H, plus like just join points, A many. And here I take a slightly larger power, so n to the, so n plus O n, n plus little of n. Yeah, so okay, it looks a bit crazy maybe, but and the same for G and H swapped. Yeah, so I'm saying you have this distance upper bound if and only if. I should imagine that I have kind of pulled this B to the other side, so that's now why I have B here and here.
Quantifier over n?
Sorry?
What's the quantifier over n? Like, is it for any n there exists?
It should be for all n here. Yeah, so A and B are fixed in this whole statement, and then here it should be for all n. But I have this little of n here that I can play with, right? So for small n, it doesn't really matter. I can hide.
Disjoint union means that you're just making new vertices.
These are just disjoint points, new vertices. Yeah, yeah.
And for G and H, I mean, like.
2 copies of the graph that are on different vertices.
Oh, sorry. Yeah. Sorry. Yeah. It's like a direct sum of adjacency matrices. I can phrase this a bit different. I can say, I can phrase it like this. I have this graph EB, which is just B points, and I take the product with G. It's the same as B copies. And the same here, I can make this a bit shorter, but it's the same. It's just an algebraic.
EB has no edges at all.
EB has no edges. It's just the empty graph. E is for empty with B points. It's like a kind of unit graph. Yeah. Okay, so it's just an alternative description. Okay, so this is here's the graph limit approach again. So to determine the Shannon capacity of some hard graph, make some sequence of each to analyze graphs, converging to it in the asymptotic spectrum distance. That's the idea.
Can you say something about the lemma, like why is it true?
This lemma, It follows from the duality. So, okay, it follows from part of the duality that I didn't explain. So the duality doesn't only characterize Shannon capacity as the minimum over the spectral points, it also characterizes something called asymptotic cohomomorphism. So it's about asking, is G to the n at most H to the n plus lambda of n? This is completely characterized by the asymptotic spectrum. And right, that's not on the slide. And from that you can get this. Yeah. That's a good question. So, okay. So, okay, now we know the notion of distance that I'm aiming for. But now you ask me maybe, well, okay, so how are you ever going to construct converging sequences? You have these weird definitions, and if this set X that you don't know, and you know, so it looks kind of complicated. And where are you going to look for graphs that are easy, right? Because you want these to be easier, this G1, G2. Otherwise, there's no hope. So we answer these questions in some way. So I'm going to explain it. So let's start by talking about converging sequences. And I'm going to use a notion of a family of graphs that I call fraction graphs. And they're denoted by E, A/B. So you might think of this as a fraction, but it's a label. It's two numbers, A and B. And this is a graph with vertex set ZAZ, ZAZ. So just 1 up to A, but you think of them as mod A. And you put an edge, so U and V have an edge. If and only if their distance, you think about it, mod A, so it's like on a circle, is strictly less than B. Yeah, so what does it look like? E5/2 is 5 points, and I connect when their distance is strictly less than 2, so 1. So that's why it's just a 5 cycle. E3/1, 3 points, connect when the distance is strictly less than 1, so it's just 0, so there's no edges. E8/3, well, 8 points, you have a bit more edges. Get a bit of a thicker cycle.
You have no self-loops.
I don't do self-loops, yeah, just to keep it clean, yeah.
Although in the powers, there are always like.
Yeah, you add them for tensor.
Yes.
Exactly, so there I have them, but then later I don't have them, because I don't want to get confused about independence number.
Yes, yes.
Or, yeah, so that's right. So there's something really cool about these fraction graphs. Like I call it that they behave as fractions, as rational numbers, in the following sense. So, right, we can think of them as rational numbers, and then there is a lemma that says A over B is at most C over D as rational numbers, if and only if there's a cohomomorphism from the corresponding fraction graph to the other. So suddenly, in the terms of ordering, these graphs behave like rational numbers. It's really strange. So they have like density also. You can always find, if you have two of them, you can always find one in between, and you can keep going. So it's a natural family to look for converging sequences, right? Okay, so that's what we do. So we have this theorem A. Pick A over B, rational number, at least 2. If you have a sequence of rational numbers Cn over Dn that converges to A over B from above, it's a condition, then the corresponding fraction graphs also converge in the asymptotic spectrum distance. Okay, so that's one way of our theorem tells you how can you construct these sequences. Here's another version of this. So what about if you have an irrational number R, and you take a sequence of rational numbers converging to the irrational number R. From above, from below, doesn't matter. Then the corresponding fraction graphs form a Cauchy sequence. Yeah, so their distances become smaller and smaller. Yeah, Cauchy sequence.
And with the F's, the distance that you defined.
Yeah, that's right. All asymptotic spectrum distance with the F's. That's right. And it's not that hard to figure out that from this, like you get Cauchy sequences that sometimes also don't have a limit. Like if indeed you pick R to be some irrational number, it's not hard to see that you get Cauchy sequences that don't have any finite graph as a limit. So some interesting things happening there. So I want to say a little bit about how you prove these theorems.
Can
there
you
is
say
an
something
infinite?
about the two?
About B?
Why the two?
2.
For any,
Two.
yeah,
Well, that's because there are no graphs between 1 and 2 in a way. So, because either a graph is just a single vertex, or it has an edge. So there are no fraction graphs between 1 and 2. That's why. That's why I do this. Does it make some sense?
okay, it's a completely technical.
Yeah, so in here, yeah, it's a bit of a technicality.
When the sequence is Cauchy, does the limit exist as an infinite graph?
I will say something about it.
Is the mapping you use here just the one you like look something like what you would expect, or
Which mapping? Sorry,
the cohomor one?
this one? It's a natural round. It's a natural map. Yeah, where you multiply with a natural factor and then you do a natural rounding.
Okay.
Yeah. That's right. Good. I will say something about how you prove these theorems. First is a lemma that's in a paper by Frana. Let G be vertex transitive. S a subset of the vertices, F a spectral point. Then you can look at G and we apply F, and we can look at this induced subgraph to S, and this inequality is then kind of trivial because of monotonicity of F, because FGS naturally has a homomorphism because it's an induced subgraph. So that's the easy part. But the interesting part is that you also have a reverse inequality. So I can also upper bound this Fg by f of g induced to S with this natural factor here, size of G divided by size of S. And okay, so I won't say much about the proof. There's a nice proof there where you're kind of covering G by copies of GS in vertex transitive. So this allows us to at least prove some sort of bound, see that certain graphs are close by, right? Because we have this relation. So that's ingredient 1, lemma 1. Lemma 2 says that if you have a fraction graph, EP/Q, we remove a vertex, then this is again equivalent to some other fraction graph, EP prime over Q prime, where there's a precise rule that tells you which P prime, Q prime are the right ones, are the parameters that you should pick. So there's a known lemma. By equivalent, we mean equivalent under homomorphism. So it means there's a homomorphism in both directions. Yeah, so we can freely remove vertices and stay within the family of fraction graphs, which is kind of strange. You would maybe not expect this if you remove a vertex from a fraction graph. It's not.
It doesn't look like a fraction.
Doesn't look like a fraction. It's not vertex transitive anymore, but it's an equivalent to a fraction graph. So there's a nice kind of there's a nice algorithm to do that. And you see also this formula appearing, which maybe looks familiar from when you're studying the GCD, for example. Consequence, if we have this EP over Q and we produce this P prime Q prime as here by removing a vertex, etc., we get this relation, right? Because when I remove a vertex, I get a graph get an induced graph with P minus 1 points. But I also know it's equivalent to a fraction graph. So suddenly I have this relation between fraction graphs, but for specific fraction graphs. They're produced in some sort of structured way. Okay, now let's apply it. So I'm going to prove theorem A. So we take A and B co-prime. So my target is A over B. I might as well take them co-prime. And then I can find these X and Y's, right? That will produce me 1. And that looks a bit like this condition in this lemma 2. But what we do here is then we can make lots of numbers that satisfy this equation, right? It's lattice kind of shape. So we have Cn, which is x plus an, and Dn, which is y plus bn, and they all satisfy this equation. And then I can apply lemma 2. Right, so now for all these graphs, I have this connection between the spectral points. And then I let n go to infinity. This ratio will go to 1. well, Cn will go to infinity, this ratio will go to 1, and we're done. That's the proof.
So in this proof, you find x and y, and you define Cn and Dn in this way.
Yeah,
So it's not like any sequence of Cn and Dn.
that's right. But so then if you have a general sequence, you need to argue that they're kind of sandwiched in between this sequence. So if some other sequence, then somehow there's always, yeah, they're kind of always sandwiched between this sequence. So you can.
You need like theorem B, say that they're Cauchy, and then and then you can say it for theorem A for any.
Maybe that's also a way of. Theorem B, let me just say something quickly. Here we do continued fraction convergence. So R is our target. You can go like around it with rational numbers called continued fraction convergence. And they satisfy this beautiful equation. And then we can apply our lemmas, get the right thing. So that all works out. Good. So limit points. So what happens there? So infinite graphs are kind of a natural candidate for a limit point. So we study that. And what's natural to do is to take a circle and then say, okay, every point is connected to like a neighborhood that's just this open interval of distance strictly less than 1/r, for example. That's kind of the right extension. You can also do a closed version that you say, oh, it's the closed interval. And that's actually interesting subtlety. They're not the same. And there's an interesting question there. So here's something we prove. If you have an irrational number R, then these two versions, the closed and open version, they have distance 0. And that's the asymptotic spectrum distance, which also works for infinite graphs. And if you have your rational numbers going to R, then your fraction graphs will go to the open version or the closed version.
We already saw it, right? Because E1 was the empty thing and not the cycle. So it should be the open version of the, right? Like when you defined E1, it was essentially the open version, right? You didn't connect.
When you do E1, yeah, that's right. Here I'm only doing bigger than 2 to avoid this.
Sorry, E of a natural number was the empty graph, which is analogous to the open option and not the closed option. So I'm just saying it's consistent in the way you define the.
Yes, but I am yes. Okay. Yeah. But that's not an irrational R, huh?
No, it's just it's for like a positive integer.
Yeah. Here I'm doing irrational.
E0, E0 of R and not E closed of R. That's your definition. So it makes sense that you will converge to the open version and not to the closed.
Yeah, but here I should point out. So the open and closed here are asymptotically equivalent. They have distance 0.
In the irrational case.
Yeah, in the irrational case. Yeah, in the Sorry.
Is this the limit of Lopez and Seged or something?
No. Well, no. You mean like graph-form type of limit, right?
Yes.
Not norm or whatever. So it's a very interesting question to understand if there's a connection. Like it's a completely different definition that I feel has a different quality. So I think they cannot really be the same. But there might be some connection one way or the other way. I don't know. Yeah. Because clearly there's some sort of analogous theory going on, right? So yeah. So here's what we know for here's another statement. So here I take rational numbers, and then I take the cycle graphs, the infinite graphs corresponding to them, the open and closed version. Their distance is 0, if and only if. So we don't know if it's 0, but this is if and only if you have the sequence of numbers coming from below to P over Q, then the fraction graphs are also converging. So there's a link between these types of convergence questions and now from below, which is the direction we don't know, and these infinite graphs. So I wanted to say. So if you want to study, you can study these infinite graphs, and it has interesting applications for finite graphs. That's what I wanted to say here. Okay, so that's just what I wanted to say about these infinite graphs.
I have another question.
Yeah.
Like on the most basic level, this is these are when it's irrational, you would say like okay, it's weird, but at least in this case, it's kind of a disjoint union of the like it's a continuous version of a disjoint union of the discrete graphs when it's rational, right? It's essentially an EP mod Q just rotated in a continuous manner. And then in this case, the closed and open, the finite closed and open versions are different. So this should be a surprising condition.
No, but
In
it's
the
less
rational
than,
case.
it's not equal to 1/r.
But
It's less than 1/r, so you have edges, you know, it's not like disjoint union of things, I think, because of the less than. If the edges were whenever two things have distance exactly 1/r,
Yeah, it's a whole, yeah, exactly, sorry. It's this whole interval, that's the neighborhood.
if it was
Yeah.
equal, then these would be like
Yeah.
disjoint graphs.
Yeah, sorry, exactly. So it's really, the vertex set is it's really a circle.
yeah, now I was confused, sorry.
Good, good. There's a lot more to say about this, there's lots of, but you have to go to the paper for that.
You don't want that.
Talk afterwards. C50, so what can we do? So the graph limit approach, there is a natural finite version. And that's maybe you don't have this full sequence, maybe you just have a graph that's an auxiliary graph H that's close to the target graph. And maybe that's already helpful, and indeed that's the case. So that's one ingredient, so I can say in a moment. And another idea that we use is to, in this auxiliary graph, to look at independent sets that are structured, namely they are orbits. Yeah, because if you think of these fraction graphs, they're all like Cayley graphs, or like groups. So you have like subgroups that might be independent sets. And it's easier to reason about them, or it's easier to check that they're independent sets, for example, right? You might notice from coding, from error correcting codes, from linear codes, right? And Shannon already had this in his paper. He had this for this 5 cycle, he had this nice orbit independent set, which is optimal. It's just this, you have this generator, you take this orbit. It's the famous independent set that he found in that paper. And okay, so I'm just going to give this overview. So what we do is we have all these small odd cycles. So the 5 cycle, the 7 cycle, up to the 15 cycle. What you can do is we find these auxiliary graphs. Okay, for the 5 cycle, we don't do anything special, but we find other interesting graphs that lie close to their target graph G. These are also fraction graphs. In there, in the power of them, we find good orbits that are independent sets and large. And sometimes these auxiliary graphs, they lie below the target graph, sometimes above. If they lie below, you directly get a lower bound on the Shannon capacity. If they lie above, like with the 5 cycle, with the 15 cycle, you need to massage it into so that you get the lower bound on the Shannon capacity of the 15 cycle. So this we do. So we get 7.3 as a new lower bound. And for the other ones, we reproduce all the best known bounds. And so this kind of method reproduces all the known bounds for the small cycles and produces a new one. Yeah, so that's this finite version of the graph limit. Good. Any questions about this? There's much detail here.
It's just how much you checked, like for the 17s and so on, like.
It gets a bit harder to find good orbits. It's not automatic somewhat. So, but we do, so maybe I should mention this actually here. We do prove that orbits are optimal for these Shannon capacity of fraction graphs when the label goes to infinity. So this we know. But for example, I don't know if these orbits are sufficient to determine the Shannon capacity, say, of the 7 cycle. This we don't know. Like we don't know if there's a barrier for that. This theorem we prove by exhibiting a good family of lattices with the right properties. Like these orbits, they correspond to lattices. And yeah, they have a good construction that proves this limiting optimality. It's interesting, it's a bit of a weight limit, right? I'm letting this label go to infinity, and then it becomes optimal.
What do you need from the lattice?
So what I mean is that these orbits, they correspond one-to-one with lattices in, but these lattices, like it's a bit like sphere packing. Right there, you can also have a sphere packing that's a lattice. And we don't know if those are optimal either. And here it's not sphere packing, it's like cube packing or like hypercube packing. But other than that, it's a very similar problem. Like hypercube packing, that's also it's called has a periodicity. And there you can ask, are lattices optimal or not?
So you mean in Z to the D, like in integers to the some finite part?
Yeah, or you can work in R to the D and then in the end make it discrete, but yeah.
So how did you find these orbits?
A search. Yeah, essentially a search, but you see some of them have more structure.
Okay.
So there's also some natural things you might want to try. We also have some other ideas of how you can do this in a more structured way with like quotient groups and like. And here we have a whole family that we found by hand. So there's several ways, but these are by computer essentially.
Yeah.
Yeah.
Is the 7 cycle, this is also the conjecture truth? Like, do you feel this should be true?
Not clear. I think it's maybe a bit unlikely this is optimal.
Ah.
I mean,
Well, you prove that it's not.
sorry? No, we don't know. This is the best lower bound, that's all. And there is an upper bound that's not optimal, that's not tight with this, which is lowest theta. But this is, yeah, I think, I don't know. Yeah. Okay, some open problems. So can we determine Shannon capacity via these graph limits? Are orbits enough? Can we have convergence from below? Are infinite graphs complete? It's also a question we don't know. And what other problems fit into this duality and distance kind of framework?
What do you mean, are infinite graphs?
So well, these finite graphs are not complete.
You mean it doesn't give me a compact space where like
I'm
close?
complete. I'm asking about not quite compactness, but
Yeah,
completeness.
so
Yeah.
like Cauchy
Yeah.
sequences actually have a convergent target, like in that sense.
Yeah, so take a Cauchy sequence of infinite graphs. Does it have an infinite graph that's a limit?
Yeah, okay.
Is there an infinite graph that's a limit for such a sequence? We don't know.
This is still not known, so we
Yeah.
don't understand this topological space essentially.
This is a question. Yeah. Good. So, okay, so now I'm going to say something about tensors. I'm going to see how far we get. We go until 12, right? So
Yeah, take some more time.
yeah, so we have done the graphs. Now I'm going to this tensor setting. It's a bit more algebraic. And it's motivated by matrix multiplication. So let's start with the matrix. Matrices we understand. We have the notion of rank, the matrix rank. It's the smallest number R, such that I can write my matrix as a sum of outer products, or you could say tensor products, or whatever, of vectors. Right? So I have UI, tensor product VI, outer product VI. And these are called simple matrices, sometimes rank 1 matrices. You've seen this. Yeah, so I want to write M as a sum of those. And that's a very nice parameter, the rank, right? For lots of reasons. It's easy to compute. It has a characterization of the form, the rank is at most R, if and only if all R+1 by R+1 submatrices have determinant 0, right? So there's this kind of algebraic characterization. Yeah, and it also has lots of consequences. So these are all nice properties. And another nice property is, for example, if we take the Kronecker product matrices, then the rank is multiplicative. Now we move to tensors, and these things start breaking down slowly. We have the tensor rank. So tensor for me is just a cube of numbers, right? Just like a matrix, but higher dimensional. Tensor rank is, well, we write T as a sum of simple tensors. So it's an outer product of 3 vectors. It's called the rank 1 tensor. And we take a sum. And we look for the best way of doing this, most efficient. Okay, well, this is NP hard to determine section R, or to determine if the rank is at most hard. So you see it's already getting a bit harder. And here we can also form Kronecker products of tensors. And tensor rank is no longer multiplicative. Yeah, so it's self-multiplicative and it can indeed drop when you take a. Okay, so what do we do with this? I told you before, we're going to look at this asymptotic rank. So you take t to the n, take the rank, nth root, you let n go to infinity. Yes, and here, by a similar, well, it's called Fackett's lemma, similar lemma, you can replace this limit by an infimum. Yeah. Before it was a supremum, now it's an infimum. It has to do with whether your parameter is super multiplicative or self-multiplicative. Okay. There's also here a duality theorem. This is what Strassen initially looked at. And it writes, so now this asymptotic rank is a minimization problem. It writes this asymptotic rank as a maximization problem over functions in the spectrum that you evaluate on your tensor. It's just analogous, completely analogous. And from here, so of course, this spectrum, I need to explain what it is, but it has a very similar definition. It's a set of functions from tensors to reals that are multiplicative on the tensor product, additive on the direct sum. Monotone under restriction is a natural notion of ordering and normalized in a natural way. We don't really need this for what I'm going to say. We also have some examples of points in there, but again, we don't know if we have all of them. So it's a kind of similar situation as for graphs. Okay, so that's the duality theorem. So let me explain the motivation and then let me tell you in what way I want to do convergence, because I'm not going to use the duality here. So again, fast matrix multiplication, we multiply n by n matrices. What's the best exponent we have in the complexity? That's the open problem. And this is called omega. So we're measuring the number of arithmetic operations. I want to know what's omega, the optimal omega. And it's between 2 and 2.3, roughly 2.37. What's the link with asymptotic rank? Well, first conjecture, omega equals 2. Maybe that's true. I hope it's true. Here's the link with asymptotic rank. There's one small tensor that you can study. It's called the matrix multiplication tensor. It's a 4 by 4 by 4 tensor. And its asymptotic rank equals 2 to the power omega. Yeah? So maybe you want to know omega. You can study it by studying asymptotic rank of this specific tensor. Okay, so that's the link. But you might also want to study other tensors. And this is where we get to Strassen's asymptotic rank conjecture, right? So here the conjecture is omega equals 2. So then the asymptotic rank will be 4, which happens to be the size of the tensor, right? It's a 4 by 4 by 4 tensor. Strassen's asymptotic rank conjecture goes much further. And it poses, well, maybe for any so-called concise tensor of size m by m by m, the asymptotic rank should be m. Yes, you have a tensor of a certain size. Concise means that's really its size. You cannot put it in a smaller space. And then its asymptotic rank is just that size. Yeah, so this conjecture is saying, oh, asymptotic rank is an easy notion. Actually, it's a trivial notion. You can easily see it. Just look at its size. Yeah, clearly, this asymptotic rank conjecture implies omega equals 2. Yeah, because it's a 4 by 4 by 4 tensor. This matrix multiplication tensor. But of course, both are open. I zoom out a little bit more, so I don't know how to solve this conjecture. I ask some other questions. I ask, what properties does this asymptotic rank have? Is it a computable notion? Is it semi-continuous? What kind of values does it take? Right? This conjecture would say, oh, it takes only integer values. Because we don't know, so I'm asking, is it integer value? And we're going to say a little bit about this.
So you wrote complex numbers, and above you wrote just some kind of field.
Yeah, good. Okay, yeah. Okay, you can do this over any field. Yeah, sorry. This can also be any field, these questions. Yeah. Yeah, exactly. If you want to make a link, you should work over the same field in principle.
But the conjecture is that for every field.
Yeah, It's for any field. Yeah. It's open in any field. So
It's easier in F2 or something?
it's not easier over F2. No. No. No, it's just, no, it's already hard there. Some of the field size is not the problem. Yeah. Or complex numbers. Right. A good question. Yeah. There's many questions about tensors that are already hard over F2.
Is it the other way around? Is there like universal field if we solve it there?
Not that we know of. There are links like it only depends on the characteristic, but that we do know. So if you, so this asymptotic rank is not going to change when you have field extensions, for example. But between F2 or C, we don't know if there's a link. Yeah, would be interesting to know. Okay, so I'm going to say something about this. But let's, like within the theme of limits and convergence, so I want to talk about convergence for tensors. But I'm not going to use this asymptotic spectrum distance now. You could do that, but it's a different thing. I'm going to do Euclidean distance. So it's much kind of maybe easier to imagine that you just have your vector space of d by d tensors, and it's just think of it as a d-cubed dimensional space, and you just have Euclidean norm and Euclidean distance, right? Can do that. Here's the theorem. This is something we prove. Look at all tensors from your fixed space for which the asymptotic rank is at most some number r. And then we prove that this set is what's called Zariski closed. And I'm going to say what that means. So what does that mean? It's a notion from algebraic geometry, right? So what it means is that this set is characterized by polynomials. It's a zero set of polynomials. Just like matrix rank is characterized by determinants. It's the same, except that we don't know what the polynomials are here. So here precisely for any d and r, you can find polynomials, find them many, p1 up to pl, so that for any tensor in your V, asymptotic rank is at most r, if and only if all your polynomials evaluate to 0. These are polynomials in d-cubed variables, as you're plugging in the coefficients of the tensor.
So D is the dimension of V.
D is the side length.
Okay.
Yeah. So d-cubed is the dimension of V.
We know nothing about them. Like
Essentially, very little. About these polynomials, we don't know much yet. Yeah.
So how did you prove it? Like,
I will say something about that. Yeah. It's actually pretty short. Sorry?
What is little l?
Little l. I don't think we know much. Maybe it's just some general upper bounds that are general. Yeah, it's a good question. Consequence, I was talking about Euclidean distance. For example, you can take a Euclidean converging sequence. And then if you look at what these polynomials do, like if they're 0 on the sequence, then they're also 0 in the limit. So if you have in your sequence that asymptotic rank is at most r, and also in the limit, that's going to happen. Just like with matrix rank, right? Matrix rank is also semi-continuous in the same way. Okay, good. Right, so we can now imagine maybe constructing a sequence of tensors that maybe converges, I don't know, matrix multiplication or some other hard tensor, and use this type of consequence. Another consequence, for this one you have to do a little bit more work, is that if we look at the set of all possible values that the asymptotic rank can take on all tensors. So all tensors of order 3, but like d by d by d, but I let d be anything I want. Yeah, so all tensors. So what kind of values come out? Well, it follows from this Zariski closeness that this set is well ordered, which means that if you have a non-increasing sequence of values, that it must stabilize eventually, and it's complete. So if you have some converging sequence of asymptotic ranks, it must have a limit that's also an asymptotic rank. These are things that follow with some abstract reasoning. I want to say something about how you prove this, actually. It's actually pretty short. Any questions about this statement?
Why do you change the distance?
Yeah, it's a good question. Just because here I can show something new or something different. But you can also use asymptotic spectrum distance. I will say that from both distances, I don't know yet how to improve any bounds on omega, for example. So, but I'm just here wanted to give a different point of view. And for tensors, I can do this, right? Because I have tensors live in this space where I have this other distance. For graphs, maybe it's not so clear. So, yeah. I could also study asymptotic spectrum distance here.
And it will provide similar results.
There will be links, yeah, but I don't know if, well, it's a different, yeah, slightly different. Yeah.
What is the best bound on omega you can prove with these techniques?
That I can prove?
Yeah.
Well, with which techniques? You mean like limiting kind of?
Just sort of this sort of general idea of asymptotic spectralism.
Not so clear yet. Like making an actual sequence. Not so clear yet. Like the best bound, yeah.
2.8 or something, Strassen.
Yeah, but then you're not making any, you're not really having any sequence. Then you're just directly studying the two matrix multiplication tensor and you just have a rank upper bound. So then we're not even using this yet. This is still a very young idea, so still has to be used. Yeah, that's what I want to tell you. Good. So how do you prove this?
One last question.
Yeah.
Do we know any other direction? Like if we know that every tensor rank is an integer, will it say something on the conjecture of Strassen?
If every asymptotic rank is an integer.
Yeah. Like,
Yeah, I think
because you said it's well ordered. Okay, say it's the integers. Do you gain any information?
I mean, it maybe doesn't immediately prove it, but it gets very close because then you have very little room left. It's not completely equivalent, but I have to think about that actually. Yeah, I think it's closely linked. But clearly, if asymptotic rank conjecture holds, then it's always an integer. It's a good question. How do you prove this thing? It goes via this step, theorem 2. We make a technical definition. We say asymptotic rank of square brackets of some set A. It's just the supremum over all asymptotic ranks of tensors in this set A. So nothing special. Then theorem 2 says if you put a bar on your A, nothing changes. The bar here means Zariski closure. So it's like you look at all the polynomials that vanish on A, and then you look at all the points on which these polynomials vanish, and that's A bar. So it's like it's the closure in the sense of algebraic geometry with using polynomials. Zariski closure. And they're linked in the following way. So theorem 2 implies theorem 1. It's easy actually. You pick A to be the set of tensors with asymptotic rank at no star. Then asymptotic rank of square brackets A is at most star. Then by theorem 2, I can put a bar to go at most star. So for any T in A bar, asymptotic rank is at most star. So then T must also be in A. So then A bar is in A. So then they must be the same because the other inequality is always the case. And so A equals A bar. So then it means this set is Zariski closed. So if we want to prove this, there's an important ingredient, which is this lemma 3. It says that if you have, it makes this link between A and A bar. It says, look at all tensors in A bar, take the nth power, with this set of nth powers of tensors in M. I can simulate these guys using tensors from A, so I take T to the N, and I take a span. So this set of tensor powers of A bar is in the span of tensor powers of things in A. Why is that?
The same n on both sides.
Yeah, same in. Here's the proof. It's 4 steps. If I want to prove that this left-hand side is in this span of this right-hand side, then it's enough to look at linear forms, because the span of a set is characterized by the linear forms that vanish on the set. And so what I need to prove, what is sufficient, is to take a linear form L that vanishes on the right-hand side on this set, prove that it also vanishes on this left-hand side. So we do that, we take that L, and we form a polynomial f that maps t to L evaluated at t to the power n. So I claim, well, that's just a function I but I claim it's actually a polynomial. And it's not hard to see. And it's a polynomial that vanishes on A, because L is vanishing on this whole right-hand side, right? So then f must vanish on A. But then f will also vanish on A bar, because that's really the characterizing definition of A bar. This is a risky closure. Then I go back to L and I see that L will actually vanish then on this on this left-hand side. Sorry. Yeah, so we're moving back and forth between L and F. That's how you do it. That's it. Good. Now here's the proof of this theorem too. So what we really need to prove is less than or equal. The other direction is the easy direction. So we take an element in A bar, T. I take the nth power and I use my lemma from the last slide to write it as a span of powers of elements in A. Some complex numbers here. Now I observe that the number of elements in the sum is polynomial in N. It's a crucial point. The reason is simple. It's because the space we're working in, we're taking nth powers. This one's empty. We're taking nth powers of my tensor, so we're living in the symmetric tensors, and there's an easy dimension upper bound for that, which is that binomial coefficient that grows polynomially in N. Yeah? So I have polynomially many factors, and then I take the asymptotic rank on both sides. So asymptotic rank of t to the n. I have sub-additivity for asymptotic rank, so I pull it inside the sum. And then I use my supremum definition to upper bound this with poly n times that supremum over all these asymptotic ranks to the power n. And then I just take nth root and let n go to infinity, and this poly n to the 1 over n will vanish, right? Will go to 1. And then you're left with what we wanted to prove. The asymptotic rank, this t, is at most the asymptotic rank of A bracket. So that's the proof. So then we're at the end. So this is the open problems for the tensors, the asymptotic ranks. So recall this notion of the curly R is all the values that the asymptotic rank takes on all these tensors, arbitrary sizes. We don't know if so we know it's discrete from above, which is this well-orderedness property. We don't know if it's discrete from below. It's an open problem. Another thing we don't know, if we look at the tensors in a fixed space V with asymptotic rank at most R, we know very little about that variety, right? It's a variety. Is it irreducible? We don't know. Degree, we don't know. Many things we don't know. And in fact, there's a link between these statements, these questions. So if Strassen's asymptotic rank conjecture holds, then it follows that, then 2 follows. So then the answer is yes. And then 1 also follows, but the answer is yes. So there's some links there. And then the last question is like similar to the Shannon capacity question, like can you use this kind of semi-continuity of asymptotic rank to bound asymptotic rank for some interesting tensors T, of course, makes an application, or maybe other tensors. There can be other problems that have interesting tensors. And that's it. Thanks.
So I have two questions. The first one is, assuming it is discrete, then does this imply better bounds on the matrix multiplication?
Yeah, it should give a tool because like it means that if you have an upper bound,
Yeah.
you can always round it.
Yeah.
Like down to the next point that's actually allowed.
Yeah, so
It would also, then you also need to know a bit about what these points are or can be, or maybe gaps between them, or like.
Means that there are only finitely many points between any two integers.
yes, but I'm asking like, does this also provide an algorithm? Like you know the R, but does this provide an algorithm to achieve that?
To get this better bound.
Yes, to get this one.
Depends how much detail you have, how much knowledge you have of this discreteness.
Yeah, the second question is, do we know the supreme is necessary to take? Like, can we use the maximum to define the this approximate rank?
You're talking about asymptotic rank, and then it's
Tensor to the n, and
Yeah.
that's the answer root of this
so
one.
that's not, yeah. It's a good question. Right, so let me go to the. It's an infimum, but it's still the question holds. And the answer is no. So in general, you need the infimum.
Okay, in general for like generality.
Yes, but also in particular for matrix multiplication.
Oh, you also know that.
Yes. So it's not enough to look at a finite matrix multiplication like a. In terms of matrix multiplication, it means it's not enough to have a good algorithm for some fixed size. You will in the end need a sequence. Yeah, it's a result by Corpus-Smith.
Okay.
So the reason for omega is equal to 2 must come from some infinite sequence of matrices, not a single one. Yeah.
An infinite sequence of tensors and like tensor rank upper bounds. But of course, there might be a finite argument, hopefully, finite construction that delivers that. So like things like the laser method also produce such like infinite sequences. So, but it will not be a finite rank upper bound somewhere on the matrix multiplication tensor. Yeah, there has to be a sequence in the end.
More questions? Okay, I forgot to say also that Jeroen will be around Thursday, Friday.
That's right.
Okay, thanks a lot.